Hello everyone. It's time to get started with the webinar. My name is Scott Emily. I have Dave Taflin with me here today. All right, so this is our the basic agenda that we'll be covering today. I spent a little introduction talking about the company and our main products, but then we'll go right into an explanation of our Sizzle technology. Sizzle is what it has dramatically sped up the performance of Tecplot 360 and by extension Tecplot Chorus. And then we'll describe how and show you how to use that in Tecplot 360 EX. And then Dave Taflin will be talking about using TechIO, which is a library that we provide, to actually write those files so directly from your CFD code or analysis code. Company is Tecplot. We were founded by the two gentlemen you see there on the left, Mike and Piri and Don Roberts, 34 years ago. That is not Dave and I. We're far younger and
better looking.
Better looking. Actually, I've been here almost 30 years, so I can't claim to be too much younger. And Dave's on the 25-year list, so we're both been here quite a while. We do visualization, visual data analysis primarily. The main products that are impacted by the new Sizzle technology that we're talking about today are Tecplot 360 and Tecplot Chorus. 360 is our flagship product. We've had it for many years. This is the latest incarnation is Tecplot 360 EX. It's far faster than previous versions, has a lot more capability, a lot easier to use. And then Chorus is the product that if you're a designer and you're doing a parametric study over a design space, it's the product you would use. Chorus is actually a superset of 360, isn't it, Dave?
Yeah, well, so 360 is bundled in with Chorus and gives you what we call the deep dive capability, where you want to see the details of a particular flow solution, but Chorus manages the overall parameter space and gives you visualization into the different, the multi-dimensional space, design space that you're operating in. Chorus helps you to navigate that.
So I want to talk a little about the motivation for the Sizzle technology. And basically it comes in fluid dynamics, wide range length scales to very large grids that are getting larger all the time. And I want to give you a concrete example of that. So this is looking out a window of a 737, and you can see this object on the nacelle, the engine nacelle. It's called a fence, and it may look like it's just sort of plastered on there as an afterthought, but it's actually placed very carefully, sized very carefully for one reason, and that is to create vortex. Actually alters the aerodynamic behavior of aircraft at high angle of attack. The reason you need that vortex is that engine nacelle is very close to the wing. It's like a big tin can. When the nose of the airplane is high, you're in a high angle of attack, and it creates boundary layer separation on the wing. And that vortex then will help keep the boundary layer attached. But you don't want it to remain attached too long because you'd like the wing to stall inward rather than at the tip. So you don't want the vortex to be too powerful. And so a designer that is trying to place and size this fence will spend time, will try to size it very carefully so it gets just the right amount of boundary layer separation at the right time. What that means is that the resolution of the grid points, it has to be very high because this is the very length scale compared to the overall length scale of the airplane. You may be talking thousands of inches in the core of that vortex near the fins, whereas you're talking tens of meters for the size of the airplane, and you have to resolve all those length scales, and that means you need a lot of grid. In fact, the grid size is and has been growing with Moore's Law and will continue to grow with Moore's Law. So doubling every 18 months. So Dave, you were just at the supercomputing conference. What are they saying about the future of Moore's Law?
The reality is Moore's Law is alive and well. We actually saw increases in computational speed exceeding Moore's Law for a few years, and all that's happened in the last couple of years is that we've dropped back to Moore's Law. Processors, individual cores themselves are not getting faster at the same rate, but we're adding more cores. The largest supercomputer in the world right now, the Tianhe 2 over in China, has over 3 million computational cores. So you can only imagine the amount of data that might generate.
So the motivation continued. The next step in the aerodynamic analysis is design with CFD. And so Tecplot Chorus is really for those who are doing this design space analysis. And what it does is it adds parametric dimensions. This is a particular case I'll go into more detail later, where they're looking at the design of the rear wing on a car. And what this does is now you're doing a large number of CFD calculations to fill your design space, or at least span your design space, and that increases the size of the data you need to analyze by orders of magnitude. We're not the only people that think this. This is a roadmap from NASA, from their vision for 2030. This is kind of busy, so let me focus in on the knowledge extraction row, which is where we play most with visual data analysis. And you can see that actually in 2020, they're predicting that we need to be able to do on-demand analysis and visualization of a 10 billion point unsteady CFD simulation. By 2025, that's 100 billion points. And by 2030, by extension, you would expect that to be 1 trillion points unsteady CFD simulation. On the top side is actually where Tecplot Chorus plays, and that is having a multi-fidelity database with thousands of CFD simulations, including uncertainty quantification. So that is what NASA is saying, and so we expect, they also expect things to be continue to grow with Moore's Law. So if you look at what this means for visualization, you can see a very simple pipeline. It starts with reading the data from some sort of storage device, and then transferring it to your GPU, CPU on the computer, and then actually displaying the visualization. The CPU, GPU is improving in performance at the rate of Moore's Law. So it's doubling in performance and speed every 18 months. Bandwidth is the same, a little slower. This is over a local area network, or wide area network for that matter. The reading of the data file, however, is only doubling speed every 36 months, much slower than the CPU and the GPU. So the data I/O is the rate determining step in the visualization pipeline, and will continue to be, and actually will become more and more so as time goes on. So what does this mean? If you do a simple analysis of what this means for time to transfer data all the way through the pipeline, the two steps that dominate are the reading off the disk, that's the blue line on the bottom, and actually transferring the data to the CPU, GPU. The x-axis here is the year. We're looking at projecting over time this changes, and just using those growth rates of 18 months and 36 months, you see that by this chart, we've already passed the crossover point. In fact, the dominating factor factor is the time to read from the disk. And at this point, you expect the current visualization architectures will actually get slower as time goes on because of that bottleneck. And if you go out now to 2030, which we looked at before, the LAN isn't even visible anymore, the time to transfer over the network, and it's entirely dominated by the disk. And you can see we're talking hours just to read the data off the disk with a traditional visualization algorithm. So what do? Basically, you need to reduce the amount of data you read from the disk. Somehow reduce it, and be reduced in such a way that as the data over time, the fraction of data you read from that file is diminishing. In other words, it's scaling linearly over time of the grid. And we do that with something we call subzone load on demand, or Sizzle for SZL. Basically, you save index file, we index the data file, save the indexed information, and load only the data you need. So it's lazy loading. A really simple example of that is if you try to apply it to a contour line in 2 dimensions. You can see this is the grid on the left. So this is a much smaller case than you would normally need this for, but as an example, it helps to understand what's going on. So what we do is we break it up into these subzones, 16 in the middle. You can see it has 16 subzones, so 16 piece original grid. And we know that we want to do this contour line at a certain value of a variable. So we've created these domains. We've actually saved the ranges for the variables in that domain. And we only load, if you look on the right, that data where the value of the contour line is within that data range. In this case, it only loads 5/16 of the total data. That means it reduces the time to load the data and reduces the memory requirements. In most cases, it's much larger, isn't it?
We were actually applying Sizzle to dimensional zones, so the scaling in most cases actually works better in 3D than in 2D.
Yeah, and of course you have far more grid in 3 dimensions. So you instead of 5/16, which is is a little better than half, you may be looking at orders of magnitude improvements in both memory usage and speed. And you can see that here. This is actually taking that same chart we did before, doing the analysis again. Now assuming that we're doing Sizzle technology. The blue line that we saw before, the traditional architecture for the time to transfer data in seconds, and the red line, which is down near the x-axis, is with Sizzle technology. And it is pretty much flat. It's growing very slowly compared to the traditional method, and it stays very fast. So it's a much better solution. And here are a few more examples. So this is several real CFD cases of various sizes and millions of cells from the 1 million cell range up to the 2 billion cell range. And the time it takes, how much faster it is than our 2000 Tecplot 360 2013 release, which was the last release before EX. And you can see that all cases are actually faster, and anything more than 8 million cells is at least an order of magnitude faster. And we actually get up to 2 orders of magnitude faster with our largest case of 2 billion cells. So we get what we expect. We expect the performance to improve over time, and that's what we're seeing, and to improve with data size, which will increase over time.
And this is to reproduce each of the plots we're looking at there, right?
That's right, yeah. So you can see, you know, a simple component of an aircraft, a landing gear with a slice up through, you know, this is a 400 million cell case, yeah.
What's that one on the upper right? That doesn't look so interesting.
The one on the upper right. We didn't have any real 2 billion cell CFD data, so that is actually a simulated data set, but it's an ISO surface.
But it's real data.
It's real data,
it's
yeah.
synthetically produced.
It's a real file.
Okay.
That's right. And if you look at that same data for memory usage, you can see and compare again to 2013 Tecplot 360 2013 R1, you can see that we would have used over 100 gigabytes in the largest case. You know, we did the test, so we did use over 100 gigabytes of memory, which is quite a bit for a desktop machine. You might have to go out to a supercomputer to do that. Our current version, even without Sizzle technology, is in the 50 to 60 gigabyte range. Still much better than before, but with Sizzle, we are down around the 2 gigabyte range.
So you can load that 2 billion cell case from a laptop?
That's right. It can be. You can do that on a laptop, even a really old, slow laptop. This is the case we showed you before with Tecplot Chorus. So this is a design study. It is a race car, and particularly they're looking at the position and angle of the rear wing. The goal of this study is to actually get the wake up and out of the way of a trailing car, because they'd like the trailing car to be able to pass, to have clean air so it can have a lot of traction for passing.
That seems contrary to the purpose of racing somehow.
Apparently it's boring if the lead car just stays in the lead the entire way. They're trying to make it easier for people to pass, so it's more interesting. These are 10 cases actually in this particular example. There's only 3, 2 positions, X position, Z position, and an angle for the rear wing, and they span the space with 10 cases, 35 million cells each. That gives you an idea of the size of it. The goal is to go through all of those 10 cases and create images with stream traces. Those are not shown here, but we've done that and done the measurements on the performance. And the result with PLT files, which is our older file, was nearly 10 minutes and nearly 3 gigabytes of RAM. Now, if you use our new Sizzle technology, it's around 2 minutes. It's much faster. It's a factor of 5 faster and much less memory. It's 0.3 gigabytes of RAM. See, the additional thing that we haven't talked about yet, and I'll show this to you in a minute, is that Sizzle will compress the file, and it saves 8 gigabytes of disk space, which is about a 31% compression in this particular case.
Right.
So it's not only making it faster and using less memory, but it's actually using less disk space. And one other example of this, remember we talked about the NASA 2030 vision and how they were going out to 1 trillion cells. So we had an internal challenge to actually do 1 trillion cells. Steady, they were talking unsteady, but we wanted to see what the issues were and actually achieve that. And this chart shows the scaling of the memory usage over time in that particular case. The lines with the symbols are various options with for memory usage, cached, not cached, and streamlines or isosurface. So we have 2 straight lines here, Dave. The first one is this orange line, which represents linear scaling, because this is a log-log plot, linear. The exponential growth in data size shows as linear. And then the purple line is on order into the 2/3 scaling.
Why are we showing that?
We're showing that because into the 2/3 is what we expect our Sizzle technology to scale, how we expect our Sizzle technology to scale for an isosurface, which is what we have in this case. And in fact, you can see that on the green line, which represents stream traces, and on the red line, which represents isosurfaces, it does in fact go pretty much parallel to the into the 2/3 line. So we are scaling with into the 2/3. There's a little blip up at the end, and we're addressing that there's some linear scaling that's coming into play, but we have a technology that we are confident will take us out to 2030 and scale as expected. So I want to do a quick demo for you of how this works in real life. So I have two Tecplot 360s up, ready to go, so you don't have to watch me launch them. I'm actually using some internal add-on capability to profile the performance in loading a layout. This is a
So a user of 360, a customer, wouldn't see that menu.
If you'd like to try this, we can give you the macro and try it. So I'm going to load a Sizzle file and a PLT file, and we're going to show you the difference in performance. This is for 183 million cells. It's a transport aircraft, and we're just loading the geometry in a slice. So that's the Sizzle side. You can see it's done already in a little under 4 seconds. And on the PLT side, it is, I'm still trying to get to where I can load it. So here we go. So you can see this is, as I mentioned, it's a transport aircraft in configuration. It's in crosswind, and we're looking at a slice that kind of cuts through one of the more complex regions of the airplane, cuts through the engine nacelles and the flaps, the slats in particular. And we're looking at, on that slice, a contour of the Y velocity, which is the cross-flow velocity. So it's in a crosswind. Okay, we're finally done over here on the PLT. So it took 29 seconds versus about 4 seconds. So we're talking about nearly an order of magnitude faster with the Sizzle technology. And if you look at the peak memory, it was over 10 gigabytes. With PLT, it's under 700 megabytes, so well under a gigabyte with Sizzle. And in fact, this includes the code space. So the amount of actual memory used for data is much smaller than that. So dramatically faster, and if you want to try this, I'm going to show you how. So there are 3 ways of doing this that we'll be talking about. The first, if you want to try it yourself, you can just load it into Tecplot and write it out as a Sizzle file. And then you can see for yourself with your data how it performs. And the second way you can do it is you can take that same process and automate it with scripts. So essentially it's launching in a script the Tecplot 360 and doing it. This would work in say in one of your CFD scripts to automatically generate these from another type of file. Pretty much any type of file that you can load into Tecplot 360, you could do this. And finally, Dr. Dave here is going to talk about writing the Sizzle files directly from your code using the TechIO library. And we have some new parallel capabilities that you're going to see for the first time today. So how do you write Sizzle files from Tecplot? It's really easy, actually. You load your data in the standard way, whatever data loader you're using, doesn't matter, except we don't currently support polyhedral grids. Then from that same menu, the file menu, you go down to the write data file, and you select the Tecplot subzone data writer in the file open dialog. So that's essentially all there is to it. It'll go through the process of creating the subzones and indexing the subzones and writing the data for you. If you want to automate that, Tecplot has a batch command capability. So you can using the command line, you can just say Tech360 with a -B. Specify the data files and then a macro file in this case, because you'll need to run a macro file to actually write the Sizzle file. Here's a simple example of how you would do that, or what the macro would look like. This is the basic macro. You can generate this yourself just by recording if you want to see how it looks. Basically specifies it's the Tecplot subzone data tools add-on that is being used, and the command is write dataset, and then you give it the file name. Now if you're in batch mode, you want to put in this quit macro. If you're running this interactively, you don't. Now if you want to automate the generation of this macro, this is an example of how to do it in a Unix shell script, just using a series of printf commands. Now the temp file name would be something you would create, either just, it can be some sort of arbitrary file name, so it's temporary. And then you'll have on the command line an input file name, which is not needed for this because that would be in the read command. This is just a snippet of the shell script, but you would also have the output file name in your command line. So this would be the output file name that's been extracted from the command line, and it just generates the macro into this temporary file, and then you could, below this, have that command we showed you before, the tech360-b, and then specify this as that temp file name as the macro command. So those are the first two ways you can do it. It's pretty easy. Dave is going to show you how to do it with TechIO.
Alrighty, so yeah, as Scott mentioned, I'm Dave Taflin. My job for the last, oh golly, year and a half has been working on our TechIO library, mostly to have it output Sizzle files. I want to recap what Scott just went over though, and whether in batch mode or interactively, we've looked so far at using Tecplot as a data converter to convert whatever sort of data file you have into a Sizzle data file that will give you all the performance speed-ups that we've talked about so far. That has the big advantage of being able to read quite a wide variety of different files. And that's particularly important if you're using a third-party flow solver like Fluent, where you really don't have control over what format files it outputs beyond, you know, the various file formats that Fluent offers. As of today, Sizzle is not one of them. So you can convert any of those formats into a Tecplot Sizzle file. It has the disadvantage, of course, that you first have to load whatever data it is into Tecplot 360 and then write it out again, which is a step that you'd like to avoid if possible. And if you're writing your own solver codes, it is possible using our TechIO library. So I want to talk to you about what that involves. So what is TechIO? Well, it's a library that you link into your program. It in supplied form, and this is installed in 360 folder, and it is a shared library or dynamic link library. And is usable in that form. However, some workers, for various reasons, prefer to use static library. And if you prefer a static library, the source code is available for download on our website, and you can download it and build it yourself as a static library on any of our supported platforms, and actually on quite a few other related platforms. I forgot to mention, as the picture shows, TechIO, the library, or szplt, the new Sizzle format, selected by a single to one of the TechIO calls that we'll talk about in a moment. However, the MPI parallel version of the library will output only the szplt format. So here are the basic APIs you call from your code to create a Tecplot data file. And this calling sequence is the same whether you're creating a PLT file or an szplt file. And you'll note that each of the APIs is suffixed with a version number. One recent one, we've had lower numbers early, but that use the newest version number to make sure that you're getting the right version of the library. In the case of DLLs on Windows, when you go to launch a program, Windows will search, among other things, all the directories you list in your path environment variable. And If you've installed earlier versions of Tecplot, it could pick up an older version of TechIO and wind up confused. So I would recommend that you always use, whenever you're coding, you always use the latest version number on all of the TechIO functions. So TechINI you use to open a new file, and this has a parameter where you specify whether you want PLT or SCPLT. TechZNE adds a zone to that file. You'll call that once for every zone. TechDat adds data to the zone. You'll call that, and these are listed in the order that you would call them normally. So TechDat adds data to the zone, and note that TechIO supports either single or double precision. We've had a request to support integer variable types, and we'll consider that for the future. But for now, single or double precision floating point values. TechNode is what you call if you have unstructured data, and this is the API you call to pass in the connectivity, the cell connectivity. And finally, to close the file, you call TechEnd. There are other APIs that I'm not showing here to add text or geometries or custom labels, but these are normally stored in layout files. And I mentioned here also that you can have multiple data files open at the same time and be writing, say, a surface file and a volume file at the same time if you want, and switch between them. You had a question, Scott?
So Dave, with the TechDat function, or the TechNode for that matter, how do you chunk up your data there? Do you have to send each data value by itself, or do you send them all at once, or how does it work?
Yeah, so both of these allow you to chunk your data any way you like. You can pass them a single value at a time or the entire array all at once. Each of these has a parameter where you tell TechIO how many values you're passing in.
And what's the advantage? Which would you do?
Well, I would use, how do I put this? However my data is stored in memory, these routines allow you to keep it there as opposed to having to gather it separately into separate arrays, thereby duplicating some memory requirements in your code.
Okay.
So here's a real simple example to create a data file with a single IJ ordered zone or structured zone, a 2D structured zone. We're calling TechINI first. Now this is a Fortran example. Our next one will be in C. We call TechINI and pass it the title of the data set, and you'll notice for each character string we append a null character. That's to make it C friendly. Then a list of variables, the file name. The next one there is the temporary directory. Normally dot is fine, but if you have some disk space issues, you may want to be able to dump temporary files elsewhere. That's relevant really only if you're creating PLT files. For SCPLT, all the data remains in RAM allocated by the TechIO library until you actually go to write the file. File format, this is where that's an integer parameter where we specify whether we want PLT or SCPLT. The file type can be full, which includes all your data, or we also support separate grid and solution files. So you can dump your examples, you have a non-moving grid, into one file and then just dump your solution variables. If you have an unsteady flow, you can dump solution variables for each time step into a separate file. Debug, another integer parameter, gives you diagnostic output if you want, and isDouble is either going to be 1 or 0. 1 if you want the file saved in double precision, and 0 will give you floating. Next call is TechZNE, where we pass the title and the zone type. In this case, we'll have set it, I'm not showing the code here, but we'll have set it to ordered. And the dimensions of the zone. And the solution time, those 3 zeros after Imax, JMax, and Kmax are ignored, but all the remaining zeros and ones there relate to advanced features, variable sharing, and so on that aren't really for this example. But you can look at the documentation to see what the options are for all of that.
Where would they find the documentation?
The documentation is installed along with Tecplot, and it's called the Data Format Guide. And it discusses not only the formats of our data, but all of the TechIO APIs as well.
And that can also be accessed from the welcome page of Tecplot 360.
Yes, as I recall. And then finally, we're going to tell TechDat how many values. As you can see, we're just dumping our X, Y, and P arrays all in at once with 366 calls. And we don't have any connectivity with an ordered zone, so we don't call TechNode, and finally we close the file with TechEnd. You'll notice each of these returns an integer value. They'll all return 0 if the call was successful and some non-zero number otherwise. The particular non-zero value won't be meaningful to you, but if you're getting one of those, it could help us or tech support identify exactly the problem you're running into. Also, setting up TechI, setting that one will give you some output, some diagnostic output to your console, so you can see possibly what's going on wrong. Now, Scott mentioned we also now have a parallel version of our library, which is based on MPI, the message passing interface. And this is specifically to support partition zones. Now, it supports unpartitioned zones as well, but writes only Sizzle files, and because we don't yet support polyhedral data in Sizzle, you'll be able to write your polyhedral data using this library. But any other zone type you can write using the MPI library. The little schematic picture there just shows an original zone, 4x4 cells that's been divided out into 4 pieces, each of which presumably is being calculated by a separate processor on a parallel machine. And each one of those processors can write out its individual partition via TechIO MPI, and then Tecplot, when it reads the file, will reassemble those pieces into a single zone. All of these calls to TechIO will write to a single file, however, and we do that using the MPI IO portion of MPI. To support MPI and partition zones, we've added 4 new APIs to the TechIO library. The first 2 are only in the TechIO MPI library, which is a separate library, but again, that's installed along with Tecplot, and source is available from our website if you want to build a static library. So for MPI only, we have TechMPI init, in which you pass it a couple of MPI-specific pieces of information. And then for partition zones, this TechZNE map tells the library which processor or which MPI rank owns which partition number for a particular zone. The other 2, TechFE partition and TechIJK partition, I dropped the 142 off of all of these, by the way, but those final 2 are also in the serial library, the basic TechIO library, and this lets you develop your partitioned output on your desktop machine, which may not have MPI installed on it, and test it using the non-MPI version of TechIO. And then you should, if that works correctly, you should expect it to work fine on the parallel machine using the TechIO MPI library. Last note there, just as only volume zones can be sizzleized, other zones can be in the Sizzle formatted data files, but they're stored pretty much the same way as in PLT files. So only volume zones benefit from Sizzle, and only volume zones can be partitioned. Now that said, if each MPI rank is holding on to a piece of a surface boundary, for example, each of them can write out its own piece of that surface data, but it will have to write it out as a separate zone.
So then the big difference between a partition and a zone is?
Well, actually, I don't understand the question.
Okay, so I guess you mentioned it. Partition, you can have multiple partitions can show up as a single zone.
Right.
Yeah, okay.
Yeah,
the
360. The 360 user will never know that the zone was partitioned. It looks the same to a Tecplot user whether it was partitioned or all written out from a single process.
Okay. Thanks.
Now some specifics. Finite element partitions. The TechIO library has to have information to know how to connect up each individual partition, and it does this through users having some ghost information. It's pretty common, although not universally true, that parallel flow solvers will apply boundary conditions by maintaining ghost cells which reside just outside the boundary of each partition's calculated cells. And in order to exchange data with neighboring partitions, each processor needs to know how its ghost cells relate to the non-ghost cells of its neighboring partitions. And similarly for nodes, it needs to know how its ghost nodes connect to the non-ghost nodes of its neighbors. I've got this schematically represented here, where the partition on the right does not have any ghost nodes or ghost cells, but does not have any ghost nodes or ghost cells. The partition on the right has one column of ghost cells and two columns of ghost nodes, which overlay the nodes as all the arrows indicate. They overlay the real nodes of the partition on the left. The TechFE partition call has some parameters where the CFD developer passes in arrays of numbers indicating which of the nodes in the current partition are ghost nodes, which of the cells are ghost cells. And then for the nodes only, the ghost cells we just don't output to the disk, but the ghost nodes we use to connect to the neighboring partition, and the developer also passes arrays indicating for each ghost node which partition owns that node, the real node, and what that node number is in the neighboring partition. Here's an example using the MPI specific calls. You'll note first we get a communicator. We're just using MPI ComWorld, but if you have a subset of MPI ranks that are doing the output, you can create your own communicator. The only rule is every rank in the communicator has to participate in the output process because we have some collective calls which would hang up otherwise. The first TechIO call is TechIO MPI init 142, where we pass it a handle to the communicator and also the identity of the main rank. This is just some rank in the communicator that you designate to do all the coordination between the different ranks. We then call we've called tech zone. I don't show it here for the sake of space, but right after we call tech zone to create a zone, we call TechZNE map to tell TechIO how many partitions are, and for each partition, which MPI rank owns that partition, and will therefore output it. Then we call for any rank, we'll call TechFE partition 142 to pass all the information that I just talked about, the partition number, the number of nodes, the number of cells, the number of ghost nodes, and a list of those ghost nodes. And for each ghost node, the partition that owns that. So ghost nodes, GN partitions, and GNP nodes are all arrays, whereas the previous parameters were all scalars. So in GN partitions, we pass for each ghost node which partition owns that node, and then GNP nodes tells you in that partition what is the node number of the real node that corresponds to my ghost node. Then finally we passed it a list, the number of ghost cells and the cell numbers of those cells. Following that, we call tech node, passing TechIO data for our partition only. And note that for any ghost nodes or cells, we are going to pass in those values. they may or may not be used by the TechIO library. And then finally, we call TechEnd to close the file, and every partition in the communicator needs to call that. Let me see if I've got any questions here before I go on. Let's see. Okay. Let's see. I had asked any drawbacks or functions not activated yet. That is losses using Sizzle. I think that question means if you move to Sizzle using the Sizzle data file format from, say, PLT, what do you lose, if anything? And the one thing that comes immediately to mind, although this is a temporary situation, but as of today, you would lose the ability to use data because we don't support polyhedral data. We support all zone types, and with the 1D and 2D zones, as I mentioned earlier, you don't really gain anything, you don't lose anything either.
Yeah, I think the other thing you would potentially lose is the node, actual node numbers, because we actually do reorder the nodes and renumber the nodes and cells as we do the domain decomposition within this to create subzones. So what you would want to do in that case, if you need that information, is actually write a variable, an integer variable. Well, I guess it'd be float in this case.
Yeah, right.
That would be the number of the node, and you can do the same thing with a cell-centered variable, which is the number of the cell, and then you can track what your node numbers and cell numbers are.
Okay, thanks. Looks like that was all, so let's move on. I should say a word about ordered. I just covered this finite element MPI example. I am currently working on partitioned ordered output for our TechIO MPI library. So any beta that you've downloaded recently won't have that feature. However, it will be supported soon. The difference will be that with IJK ordered partitions, you won't have to enter any ghost nodes or cells. You'll just enter the index ranges of the overall zone that are covered by a particular partition. TechIO will do all the logic to figure out how those partitions are connected together using those index ranges.
Excellent.
So I'm going to hand it back to Scott here to summarize what we've covered today.
Thank you, Dave. So just in summary, we talked a lot about the Sizzle technology and in particular, if you remember anything, remember it's faster, uses less memory, and it compresses the finite element files. And there's three ways to create these files that we showed you interactively using Tecplot 360EX in batch mode, using 360EX in a shell script, or it could be TechIO. We also are always interested in getting more data and working with, especially with the code developers or users, to make sure that our TechIO, for instance, is creating good files, is easy to use, and that we actually are getting the speed ups on all the data types that we expect in use cases. So if you have any questions or just want to chat about it, you can shoot me an email, and Dave or I will give you a call and we can figure it out. All right, excellent. So thank you for listening.